Okay, this is a little video for C2 on scalar multiplication and also properties of vectors. So actually we're going to start with properties of vectors. So we've got some properties listed here that kind of got cut off your screen, sorry. But it says commutative, associative, and distributive. It's just missing the C-A-D. And we're going to look at what those properties mean when we're adding or doing dot product or cross product. Okay, so it turns out when we're adding or subtracting vectors, order doesn't matter. So I can add vector A plus B, and that will equal the same thing as vector B plus A. So that's good to know. Dot product, and it's going to equal the same thing as vector B dot A. But unfortunately, cross product is the part that's different. So for the cross product, if I take the cross product of vector A cross B, then that's not going to be the same thing as vector B cross A, but it is going to produce an opposite vector. So if I just stick a negative in front of this, then they can be equal. So if I do the cross product of A cross B, and then I do the cross product of B cross A, I will just produce an opposite vector. Meaning, if my two vectors, A and B, look like this, and that's my cross product of A cross B, then when I do B cross A, my cross product is just going to go in the opposite direction, same magnitude. Okay, so that's the first property. The next one, associative, just shows us kind of like a order of operations bedmas thing. So if I'm going to add vector A plus B, and then I want to add vector to C, well, turns out it doesn't really matter what order I add them in. I could do vector B plus C first, and then add it to vector A. And we'll compare dot product with a scalar. So let's say we have a scalar K, and then we're going to do the dot product. So we're going to do the dot product, then we're going to multiply the answer by a scalar. Well, it turns out it doesn't matter when you multiply the scalar. So you can multiply the scalar by A first. So like multiply the whole vector A by 2, and then do the dot product with B. It's going to give you the same answer. Or you can multiply the scalar by B first, and then do the dot product with A. It doesn't really matter what order you do things in. And then the cross product. So if let's just look at a scalar. So if I had a scalar, I'm going to show you this in two ways. If I had a scalar, and then I had vector A cross B, I can expand that or split that up differently. So I can multiply vector A by my scalar and then do the cross product, or the same as the dot product. So I can do multiply my vector B by my scalar and then do A cross B. I guess I'll just show you this too. So I can, actually no, I'll leave that for distributive property. Yeah. Okay, so yeah, the last one is the distributive property. Okay, so how that works for addition. So let's say we had some scalar, and then we're going to do A plus B. Well, it turns out we can distribute that scalar amongst these two things. So we can do a scalar times vector A plus the scalar times vector B. Oops, sorry. Let's just go over that. Okay, so that's the distributive property, and same with the dot product. We have A dot. Then we can do the distributive property to that. So our answer is A dot C. A dot C. So we do it like that. Cross product. Okay, so let's say we had A cross B plus C. So it's going to work the same way as the other two have. So we can just distribute it like this. So it would be vector A cross vector B plus vector A cross vector C. Okay. So that's our vector properties. And then scalar multiplication, I don't know what I wanted to say about that. I feel like, yeah, if you have a vector A, I kind of covered this in the last one. That's, you know, whatever it is. And then you had some scalar you wanted to multiply it, so you wanted to figure out, hey, what's negative 3A? It just means the negative 3 is what you multiply each coordinate in your vector by. So all of those would get multiplied by negative 3. And then for geometric vectors, I don't know, if we had a vector that had a magnitude of 3, so, or let's just say this is vector A, and we wanted to represent, hey, what would 2A look like? Well, it would look the same as A, but be twice as long. Or what would this vector look like? Okay, so it'd just be going the opposite direction. So that's all scalar multiplication is.